Hello everyone, I normally don't voice over my videos, but this time the subtitles will be too hard to follow. Anyways, this is my Turing machine. I assume you know what is it, but if you don't, it's a machine that has a tape with symbols it can read, and then it replaces them with other ones. It can also move the tape left or right. As you can see, the program is done and the machine has stopped. Now we're gonna explain how it works. For this reason, I made a quick overview. First, the machine does stuff based on the symbol it has read, and the state it has is some registers inside. The state is a variable, and at the beginning of the program, it needs to have some initial value, say 000. Then, the machine is ready to read the symbol from the tape. After doing this, it has already collected all the input information, and in order to do anything based on it, it uses something we call a truth table. The truth table has rows for each combination of state and symbol, and each row contains a 7-bit instruction. So it's basically a source code of the machine. Now, based on the first 5 bits of the instruction, the machine goes into a new state and prints a new symbol in place of the one it has read before. Then it moves the tape left or right depending on the bit 6 of the instruction, and if bit 7 is high, it exits the program. If the program continues, the cycle starts over again. Now, let's see the real-world implementation. The symbol reader is connected to 2 of the registers. The remaining ones are for the state. When the reading pin goes up, it sets the register. When it goes down, it resets it. Like this. Set and reset. The mechanism first resets both registers by pulling both pins up, and then it only sets the ones with a logical 1 on their part of the symbol. First we reset all of them, then we set the ones we need to. When the reader is not reading, the pins are in a neutral position. At that time, the registers just remember the last state they've had. Now the grey register got set and not the blue one. Here's a close-up of the mechanism. It's actually very simple and does some redundant things, like lifting the reading pins to reset the registers. It costs quite much energy because they're heavy, but that's not a big problem since there are only 2 pins and not 7 like for reading the instruction. There's also a similar mechanism at the display. After reading the symbol, we need to access the truth table. These 5 pins are the previously mentioned registers. They've been set based on the symbol and the current state, and only the ones set to logical 1 are a part of the mechanism. And how does this mechanism work? Well, the pins are pushed while searching for the proper address on the back of the truth table. When they find it, the searching process stops. The addresses look physically like this. Yes, these are binary numbers from 0 to 31. I mean, a binary 1 is represented with a hole, which may feel strange, but the sensor actually detects the holes, like this. It always finds the first matching address, that is, the smallest binary number with 1s in the places of the searching pins. This is what I mean, by the way. This address is also the correct one, meaning it has 1s at the places with the pins and 0s everywhere else. Indeed, this is the smallest number the sensor will find, because replacing in it any subset of 0s with 1s would make its value greater by a sum of some powers of 2. So the first address that is found always has holes exactly where the pins are. These 2 switches trigger the searching process. It's performed if and only if both are in the on position. Here I made an animation. The one on the left is called searching switch number 1 and is connected to a mechanism that activates the sensor. Here is a close-up. The sensor is connected to another mechanism. This mechanism is connected to the searching switch number 2, that is, the switch on the right. When the address gets found, it turns this switch off and the table stops moving. When searching is done, the machine reads the instruction and sets everything based on it. Here you can see the reading pins. Each of them has a handle so that it can be handled. Each one is also connected to an axle. Three of the axles are connected to the remaining registers. And they're also connected to the display. Two reading pins are for rewriting the symbol. And one decides whether to move the tape left or right. However, this was only a simplified version of the mechanism. It doesn't have all the functionality. For example, the registers 0 and 2 do get set right now, but register 1 still doesn't get reset. You can see it's constantly in the same position as at the beginning. The only way to reset it is to pull the orange pin up, like now. Did you see that? Other registers can also be reset by pulling other pins. We'll now update the mechanism. Now the pins that haven't fallen get pulled up. Now this is the mechanism that is actually used. The mechanism is controlled by this axle. Searching switch number 2 has also a second function. When it's on, rotating the input doesn't do anything visible here, but when we turn it off, the big gear starts rotating. This gear drives all the parts of the cycle except searching, that is, reading the symbol, moving the tape, and setting the registers. The time when these functions are executed will be further called main part of the cycle, or MPOC. I made this acronym because we're gonna use it frequently. During MPOC, the searching process is off, so we're gonna connect this to the searching switch number 1, the one that disables the searching sensor. Now, the sensor gets disabled as soon as it's not needed. This is important because the registers can be set when it's enabled. As you can see, I'm trying to move them and nothing happens. But now everything works just fine. Searching switch number 2 gets switched off when searching is done, so at some point it needs to get switched back on. But this would normally stop in POC. That's why there is a LED switch. It keeps the output on even after searching switch number 2 stops powering it. It's activated by the last table reading pin. These three axles control the functions of the machine during MPLC. But what controls them? After a short disassembly, we can see this mechanism with an orange part. This part can switch between the three functions. Everything is controlled by a stepper mechanism. To show how it's so precise, I made another animation. Namely, the outputs of the gearbox always make exactly 3 rotations. That's because the gearbox has extra space to catch the gear. As you can see, this part is rotated, while this one is not. The gear always ends up in the same position, because each cycle the gearbox makes a whole number of quarter turns. That's how the functions are executed in the right order during MPLC. There's only one thing left. Namely, we still need to home the truth table. That's why while the tape gets moved, this happens. This is the table homing switch, and it makes the table driving axle rotate in the opposite direction. There's a sensor at the end of the truth table's bed. It activates a really fast working mechanism. Yes, that's it. In case you didn't notice, I'll make a replay. The table homing switch is connected to the mechanism of the searching switch number 1. Because of this, searching starts only if MPLC is over and the table is in the home position. That is, both of the requirements are met. Okay, I think that's all. So to sum everything up, I made this cool looking diagram. Enjoy!